deployment of SWAT. How long does it take to fully deploy the solar arrays? Is this spring back effect normal in solar array deployment?
But I have to say, I'm not an expert on these solar panels because they were built by our French partners. But the solar panel deployment does have about 2 phases. There's like an initial kickoff. So the solar panels are kind of kick off. And then there's like a spooling, like a wire that gets spooled in, and that deploys the solar panels fully. It takes like 20 to 30 minutes, about in that order of magnitude, to deploy. But that is relatively quick when you want to be very careful in space and make sure these work. But our partners have done this many times, so it's exciting to see that they successfully deploy.
And it takes a little while, doesn't it, Christine? It's not, you know, just automatic in 60 seconds they're deployed. I mean, it does actually take some time, and even some time over the course of days.
Yeah, so we don't always have communication with the satellite, and so you carefully plan activities so that you know that you're going to do really big activities like that one, like deploying a solar panel. You do a lot. You could do preparation for weeks just to do it for like 30 minutes to deploy. And the other part of it is you don't want to break anything, or you don't want anything to snag. With deployables, snagging is always a concern. And so we design away the chance of snagging, but the faster you deploy something, the more likely something is to crack or snag or something. So you want to kind of do it in a controlled way as much as possible. But that initial kickoff is important because you kind of want to get away from the body as quick as possible.
Awesome. Okay, so next question comes from Travis Ramirez on YouTube asking, if you could have included one more instrument or experiment to do with SWAT, what would it be?
Okay, so I'm an engineer. I like engineering and building things. I'm not a scientist, so I don't have a good understanding of what sort of climate science might be the most valuable. But SWAT creates a lot of data, and that data is hard to get to the ground because we can only talk to SWAT during some time. We don't have live streaming from SWAT all the time. And so what I would do is actually add another technology called optical communication to SWAT, which is essentially using lasers to communicate data back to the ground. And that helps us get a higher bandwidth of data to the ground. So I think it'd be really cool to have SWAT communicate with lasers back to the ground. Space lasers are always kind of fun to think about. But that's what I would add. But I'm not a science expert. I'm just an engineer who wants as much data as possible.
I think lasers in any capacity sounds really cool.
Absolutely. And it's a technology that JPL is going to launch on the Psyche mission soon. So it's coming. It just didn't make it onto SWAT.
Great. Next question comes from Rachie on Instagram. What made you want to become an engineer? And do you have any advice for anyone out there who is interested in this field?
Yeah, so I was super, super lucky to be a student in the Girl Scout sailing program in Houston, Texas, as well as a FIRST robotics student. And those two programs, well, sailing taught me aerodynamics and like mechanics of a sailboat, and the robotics taught me engineering and a little bit of that. And so I got exposed to a lot of STEM concepts without even knowing I was being exposed to it. I just thought I was sailing, and I didn't know I was learning STEM. And through those programs, I slowly learned that I wanted to be an engineer. Now, the advice I would give to someone is to follow your curiosity. I was really privileged to have access to those programs, but if you're curious about something, follow that curiosity, and don't let a lack of skills always stop you. There's plenty of resources online, on YouTube, on all sorts of places where you can learn something, and don't be intimidated that you might not know how to use a tool. Someone is always willing to teach you, or you can maybe find a resource in your library to follow your curiosity and learn the tools you need to follow your curiosity.
That's so brilliant, Christine. I was a Girl Guide in Canada as well, and so I absolutely loved even just going on nature walks and just getting out there and figuring out what it is that you're passionate about and what you love.
Yeah.
All right, we've got some more questions coming in. So how far from Earth is SWAT? And that's from Akawi Returns on Instagram.
Yeah, so SWAT, as you said, is about 550 miles above Earth. It's kind of in a low Earth orbit, which allows us to collect that really good science data without being too far away.
And is it always going to stay at 550 miles?
It'll be about there for the rest of its life, but it will switch from like a holding orbit for calibration to a slightly different orbit that lets it see all of Earth's surface water.
Okay. And then we've got another question coming in from Jeremy on Instagram. It's hard to tell from photos how big SWAT is. Can you help us better understand how big this thing is? And it's hard too, because this is the 1/3 model behind me, and you can't even hardly see it because basically it's just the center part of it, and it's not everything that's included.
Yeah, so a lot of people will compare it to an SUV before it deploys. So it's about the size of like a really large SUV before it deploys. When I think about it, I think of it more of as like a small school bus. So that's about how it is when it's on the top of the rocket. And then when it goes to space, the solar panels and the antennas, the Karen antennas deploy, and it ends up being about the size of a half tennis court. So it becomes quite large, like it has a large footprint once it's in space, but that doesn't fit in the rocket, so it has to kind of go up all packaged together.
And then everything slowly, surely, as it's been doing over the last 40 days, starts to unfold.
Yeah, absolutely.
Piece by piece. All right. So now I know that you are a big advocate of women in STEM, and I heard you talk a lot about your year in France. We got to spend a lot of time on Instagram together, and I loved seeing all of your posts. So tell me a little bit about how that experience was, spending the year in France working on SWAT with that team. And it was a team, the mechanical team was made up of women, which you also said was just fascinating.
Yeah, absolutely. So me, along with some of my colleagues, we actually moved to France for a year to help integrate the American half of the satellite with the French half of the satellite. And that was an incredible experience. We had worked with our French partners remotely over the pandemic, and meeting them in person was really exciting. And personally, it was really exciting because I got to explore France, and I got to work in a new facility and see how they built satellites and kind of mesh JPL's processes with our partners' processes at Kness. So that was exciting. And then the JPL mechanical team is mostly women, and we actually got to go to France and meet many of our counterparts who are also women. And STEM is a male-dominated field, but it was exciting to see like that some of the Kness project was managed by an awesome woman. And I love rock climbing, and I actually talked to her, and she's a manager high up in her career, and she had grown up rock climbing in France, and we got to bond over that and just learning and seeing all of our colleagues on the French side and the American side kind of merge cultures and work together in various ways was really exciting.
And science has no boundaries, and that's what's so amazing about projects like these.
Absolutely, especially earth science. We all care about making sure that Earth, we know as much as we can about the climate, and so our partners are as invested in that as we are.
Well, thank you so much for joining us here today, Christine. It's been such a pleasure working with you, and I know that you can't wait for that data to come down. Every little piece that comes down is just as exciting.
Yeah, we've gotten the first little bits of data, but I can't wait for the satellite to be calibrated, and we'll get real data. And it's been an honor and a pleasure to work on SWAT with the entire team here at JPL and across the ocean.
Well, thank you so much, Christine. And thanks to all of you guys for being here with us today. If you want to learn more about the SWAT mission, you can follow us here at NASA JPL and also at our sister station at NASA Earth that Christine has been on today. And it's a really great mission, so I hope you have the chance to go back and forward with us as we look forward to that first science data coming down here in just a few months. And remember, at NASA Earth Science, your home is our mission. Thank you so much for joining us here today, and go SWAT!
Go SWAT!
10 years ago, we established our Out and Allied Employee Resource Group at Johnson Space Center.
It was really hard to feel that I was the only person in the world that didn't make sense.
I didn't know what the reactions would be.
I think you have to love yourself, realize that you're a good person, realize what you have to offer to the world.
It gets better.
It does get better. It really does.
And it did get better.
And liftoff.
This is really just us doing our job.
Touchdown confirmed. Perseverance safely on the surface of Mars.
I think the progress since I was like in middle school and high school is pretty astounding.
So it was nice to be able to have a support system here at work.
Since 2011, NASA's employee resource groups have grown. NASA's partnerships have evolved.
Liftoff of the Falcon 9 and Crew Dragon.
We've diversified.
And now we're even stronger.
The support system is strong and it's there, it's needed, it's visible. We still have a little ways to go, but I think as years go on and we're casting our net wider and wider.
There's nothing wrong with you if you're in the LGBT plus group. Don't be afraid to be yourself, and there are people out there that will support you.
We're stronger together. We have our eyes set on the moon and beyond to dare, unite, and explore the universe.
Right now, we need the strongest candidates from across the country and around the globe. We need female leaders.
We need gay scientists.
Hispanic doctors.
We need black engineers.
We need the best.
The best.
The best.
It does get better.
And we still need better.
We are family.
We thank those who came before us and want to keep paving the way for those who come after us.
We stand on the shoulders of our predecessors,
who fought hard so we could focus on the future.
If you're alone, we feel you.
We were you.
If you feel different, we understand.
Our message to you, to all of us, 10 years later, is that we belong.
We belong.
We belong here.
And we're not going anywhere.
But wait, we're going to the moon.
You're right. We're going to the moon and Mars.
So work hard.
Stay strong. And join us.
NASA stands in solidarity with our LGBTQ+ employees and its allies because this commitment is necessary for humanity to continue to discover and expand knowledge for the benefit of all.
Hi, I'm Nikki Fox, and I'm in charge of all sun science here at NASA. This is Ask NASA, and I'm here to answer your questions. Is the sun a ball of fire? No, it's not. We know that the sun can't be a ball of fire because we need oxygen to be able to have combustion, and there's no oxygen in space. The sun, however, is a giant nuclear furnace. The core in the very center is very, very similar to a nuclear reactor, and all of these particles get squashed together, and there's a huge amount of pressure, and they undergo chemical reactions, and so there are very different layers as you move out towards the edge of the sun. Why does NASA send missions to the sun? Because the sun is the most important thing in our solar system. The sun generates light, but also a tremendous amount of energy, and it sends all of this material to us here on Earth. And so we live in the extended atmosphere of the sun. We've looked at the sun in every different wavelength, but recently, NASA launched the Parker Solar Probe, which is a daring mission to go into the very atmosphere, the very heart of the atmosphere of the sun. So I have a model of the Parker Solar Probe spacecraft here. Could I get some sun in here, please? So the important thing is, as the spacecraft moves around the sun, the heat shield has to remain pointed towards the sun at all times. So the heat shield, the front of the heat shield, will get to about 2,500 degrees Fahrenheit, but the main body of the spacecraft is nice and cool at about 80 degrees Fahrenheit, which is a bit like a balmy Florida evening in August, I guess. And that's Parker Solar Probe. Thank you. Good. Like you are. So one of the things that we discovered with Parker Solar Probe on the very first orbit was switchbacks. Switchbacks. If only I had a model of the corona. Oh, thank you. So switchbacks are really reversals in the material coming from the sun. So the sun has a magnetic field, and that is continually moving away, or so we thought, continually moving away from the sun. But what we found with Parker Solar Probe is this magnetic field actually kind of reverses on itself and makes an S shape. And we call that a switchback. It's hard to twist a magnetic field. It's like trying to twist a rubber hose. It's hard. And so somehow there's this energy going into the magnetic field that's causing this S shape. And when it releases, it's letting all of this excess energy out into the solar wind. Thank you. Studying the sun is really important as we get ready to support the Artemis mission. We're really protected here on the planet by our magnetic field and all of that atmosphere around us. Our astronauts, when they will be on the moon, and of course as we journey further to Mars and beyond, we'll be traveling through the solar wind and living really more in the atmosphere of the sun. And so it's key as we go forward to the moon, to Mars and beyond with our Artemis mission, that we really understand the source of energy in the heart of our solar system. Parker Solar Probe on her final closest approach, after she's done all of those Venus flybys, she will be at about 3.9 million miles above the sun's surface. We have many materials on Parker Solar Probe that don't melt despite how close they are to the sun. In fact, that was one of the big technology challenges for us, to find materials not only that don't melt, but can actually withstand the incredible change in temperature, because Parker goes very close to the sun and then comes out around the orbit of Venus, which means that all these materials go really hot and then really cold at least 24 times. So the critical thing for Parker Solar Probe, of course, is to keep that heat shield pointing at the sun. At some point, she will run out of fuel. At that point, unfortunately, she will start to turn, and the full illumination of the sun will hit parts of the spacecraft that are not designed to see the sun. And so she'll break up into large pieces, and then they will get gradually smaller and smaller until they become really tiny. And so I like to think that she will become part of the corona, and she will orbit the sun forever. So honestly, we don't know what new science we're going to expect. We've already seen unbelievable stuff on our first couple of orbits. Science is a voyage of discovery, and that is what Parker Solar Probe is doing. She is going into a region where we've never been before. And so honestly, we expect the unexpected. My favorite aspect about the sun is it's a star, and it's a star that we can go and visit. And so you think, you look up in the night sky, you see all of those stars, and yet we're actually sending a spacecraft right into the atmosphere of a star right now. And that means we're going to understand more about other stars in our universe, and that's amazing.
Do you have a question for NASA? Send your questions to our experts on Twitter using hashtag AskNASA.
It's extremely exciting. In my lectures, there are always young people in the audience, and they always want to know when they're bringing it back, and I always say, I don't think ever. I think NASA, they realizes that they have two marks, so to speak, but somehow they can be made to coexist. We had to analyze what had been done by NASA in the past. Finally, we realized that we had to have a unifier, something that was very strong, hold it all together. So over the process of working on it, over the first month, I think we got simpler and simpler with our solutions so that it would work miles away on a T-38 or a rocket or a space shuttle. We were trying to embody in the logo innovation. The organization still had aeronautics as well as space, and so that you see a kind of nose cone design inside of the A's and propulsion, kind of upward thrust. Great simplicity, but still movement.
Roger, roll, Discovery.
The term worm came out of Florida in a newspaper down there, and it was meant to be derogatory, and I personally thought it was very derogatory. And eventually, over the years, the worm became a term of endearment, but it wasn't meant that at all in the beginning. When they started producing apparel a couple of years ago, they found out how young people in particular really like this program, and so they've allowed it to kind of come back to life on its own. It's validation, I think, of the sort of timeless approach that we brought to this. Space is about the future, and if we can still hang in there, and if it still represents that, then it's quite a victory, I think. Aesthetics aside, the goal was to do that, to hold up for decades, and apparently it's got better legs today than it did then.
NASA celebrates LGBTQ+ Pride Month.
Hello, I'm Dr. Valerie Neal, a space historian here and chair of the Space History Department. We are in the Moving Beyond Earth Gallery at the Smithsonian's National Air and Space Museum for a program that is sponsored by Boeing Company. We would like to welcome our online audience today, our audience on NASA television, and give a special welcome to students who are here from one of the Washington, D.C. schools, the Whittier Education Campus. We're glad to see visitors from the museum here as well today also. We've gathered today to have a program on Sally Ride, curating her life, because the museum has just accepted a generous donation of personal possessions and papers from Sally Ride. And as you know, Sally Ride was America's first woman astronaut. She was not a girl who aspired to be an astronaut, because when she was growing up, only men were astronauts. But just as she was finishing her education, she realized that NASA was recruiting women for the first time, and she thought, I can do that. Because she was a scientist. She was interested in physics and astrophysics, and space had a great deal of interest to her. She applied and was selected in 1978, along with 5 other women who were the first women selected in the United States to be astronauts. And then she was further selected to fly on the 7th Space Shuttle mission in 1983 as the first woman in space for the United States. She flew again the next year with another first woman, Kathy Sullivan, who did the first extravehicular activity. So together they both made history, and Sally especially became an iconic object. She became a celebrity overnight, something she had never imagined or really prepared for. And she became a national hero, a role model for millions of young women, girls, and even adult women who now realize that whatever you aspired to be, if you worked hard, you could achieve it, even achieve being an astronaut. However, Sally herself did not see herself as an icon. She saw herself as a scientist and an educator. And when she left NASA, she went back into the world of education and spent a full 25 years teaching physics at the university level and then founding Sally Ride Science. So we're here to honor the collection that we are receiving because it represents many aspects of her life. Unfortunately, Sally died too young and too soon in 2012, and it has fallen to her very best friend, her executor, and her partner in tennis, in writing, and in life to curate her life, to be the custodian of her possessions and papers, and also her life story. And we have with us today Dr. Tam O'Shaughnessy, who is that person. Dr. O'Shaughnessy is herself a scientist and an educator, and she is now the president, co-founder, and CEO of Sally Ride Science. And it's through her generosity that the museum is accepting a collection of almost 200 objects belonging to Sally Ride, and also boxes and boxes of papers, books, notebooks. We also have today Dr. Margaret Weidekamp, who is also in the Space History Department. She is responsible for about 5,000 of the 60,000 objects that are held by the museum. And Patty Williams, who is our acquisitions archivist, and she's very active in collecting the papers of people both famous and less famous. And we're going to hear from all of these women as we go through our program today. All four of us work together to assemble this collection, and we've been working together for the past 2 years to reach this point today. I should say that during the program we will take questions from the audience, both the audience that's present here and our online audience. And we're going to start by talking about what it means to curate a person's life. How does one look at objects and figure out what stories they tell? Which are the memorable stories of that person's life? And more particularly, what choices do we make? What decisions do we make? And why when we're assembling a collection? And even beyond that, how do all these things that are displayed in a museum come into the museum's possession? We thought this would be an interesting topic for our audience to consider, and it's something we certainly have thought a lot about. Before we start talking ourselves, though, let's let Sally tell us a little bit about herself in her own words.
I was sort of a typical Southern California girl growing up. I loved sports. I was outside all the time on the tennis court for probably 2/3 of my waking hours. But when I was inside, science and math were my favorite subjects.
Main engine start. We have main engine start and the ignition and liftoff. The liftoff of STS-7 and America's first woman astronaut.
Just an unbelievable privilege that I was able to experience spaceflight at a time when so few people in the world have had that opportunity. I cherish that every day.
Tam, since you knew Sally the best, would you like to start by talking about this process that you've gone through over the last 2.5 years?
Sure, absolutely. Valerie said, my name is Tam O'Shaughnessy, and I am currently the co-founder and CEO of Sally Ride Science, which is a science education company in San Diego. And probably more importantly, I was Sally's, we met when I was 12 and she was 13 years old playing tennis in Southern California, and we became good friends and later became partners in life. And our interests were so similar, we also started writing children's science books together and then co-founded a company with some of our friends to try to make a difference in science and math education across our country. So we started Sally Ride Science. And as Valerie said, Sally died way too early. Most people in her family, her grandparents and so on, lived into the 90s, and Sally was prepared to live that long and do many more fun things, but it was not to be. And when she died, I quickly realized that I wanted to make sure that her legacy and who she really was preserved, for future generations. And so what I did is I had no idea how to go about doing this. And I ended up calling our friend, Senator Barbara Mikulski, the good senator from Maryland. She's just this wonderful, feisty woman, and Sally and I would call on her for advice on occasion. So I called Barbara and asked her, Sally was a great saver. You could almost say she could be on one of those hoarding shows, but it was pretty borderline. But she saved everything from the time she was a very young kid, tickets to Disneyland, her tennis card from the Southern California Tennis Association when she was 12 years old, and so on. But it ended up being just this treasure trove of stuff that was, important for me to preserve and do something important with. So Senator Mikulski recommended the Smithsonian, the National Air and Space Museum, as the perfect fit, and put me in touch with Valerie. And Valerie and I had a very wonderful telephone conversation that kind of gave me the confidence that I had found the right home. And then what happened is that Valerie, Margaret, and Patty, we have the two curators and space historians that deal with the three-dimensional objects. And then the archivist, I just learned that you say archivist, not archivist, which I've been saying for my whole life. Anyway, Patty Williams, the archivist, would be responsible for going through all of Sally's papers, very cool stuff from, her essays on Shakespeare that she wrote at Stanford to her notes on the Challenger accident investigation and some of her, her observations of some of the other members of the investigation team and so on and so forth. So these three came out to my home, and this was less than a year after Sally had passed away, so I was still kind of ragged. But I was excited to have them come and look through all of Sally's things. And I'd already been trying to organize our home and just kind of figure out what was what. And Sally was actually a very organized person. And she had a physics study where she kept her all of her physics books from high school and through college. She would never get rid of them. She loved her physics books and her space books. And that's really where she kept most of her NASA films and checklists and just all of this stuff. And then we had a study together that was kind of the Sally Ride Science, our company study, where we kept a whole bunch of other stuff. So anyway, I tried to organize stuff, and then these three came, and the first day that they were at my house, we basically sat in the living room, drinking tea or something, and just talked about, what I remember clearly is just the respect for what were my goals for giving Sally's possessions to the National Air and Space Museum. And we all just sort of got along, and there was this level of trust and belief that we could put together something that would be important for future generations and do it well. So I just, what I was concerned with is I wanted an institution that was going to be around for centuries. That's the Smithsonian for sure. And I also wanted a place where the people who work here care deeply about Sally, but not just, Sally was an astronaut for 10 years. That she had 31 other years that she did other things. She was a physicist, she was a science writer, she started a company, and she was very important across our country with space exploration and the two accident investigations, and she advised presidents, and all of that stuff is important. Anyway, I just, these three sort of became friends for life, and I could not be more thrilled that this is the home for Sally's stuff. Basically, that was her tennis racket when she was like 13 years old. So this was her telescope when she was a kid. So anyway, I'm thrilled.
Well, we were thrilled too, obviously. I'd like to turn now to Margaret, who was the principal collecting curator. And I'll remind the audience that we're going to have questions in just a few minutes after Margaret speaks. So be thinking about what you might want to ask Tam or Margaret as we go along. Margaret, we'll turn it over to you.
Okay. Well, I work with what we call our social and cultural collection, social and cultural dimensions of spaceflight, which basically means our memorabilia of the actual space program. That's the biggest part of this collection. And so when I have an opportunity like this to be able to go into someone's home and to think about what do we want to collect, I'm really trying to think about, what are the objects that we want to have at the museum so that generations from now, when people want to know the story of the people who make actual spaceflight happen, they're going to have the right objects that tell that story. And what you're seeing on the screen is a bit of a selection of the kinds of things that we were able to bring here from Sally Ride's personal effects. And so I knew right off the bat that we were going to want to add to what the museum already had from Sally Ride. So you'll see behind me, if you're in the room, we have Sally Ride's flight suit that was given to the museum in the 1980s, and that's on display here in this gallery in the Moving Beyond Earth exhibit. And I knew that we wanted to take that, and then we also wanted to really build into a whole life. Who was this woman? And I actually started my career as a women's historian and later got interested in space history. So I was really aware of how pivotal Sally Ride was as an American woman and how much her story dovetailed with really important stories about the women in the second half of the 20th century. So for instance, the fact that she played organized sports as a youth and that she competed in tennis tournaments, and so she and her friends were part of this, and that really tells us a story about women as physically active beginning to get into organized sports, and really she predated unfortunately for her, the transition that was Title IX, which said legally that you had to have equal funding for men's and women's education, really, and often it's focused on the athletics, which meant that she was one of the very best tennis players at Stanford and did not have a scholarship because there was no such thing as an athletic scholarship for women at the time. So being able to bring in the tennis racket that you see in front of you and also up on the screen began to allow us to tell some of that story. And it really was an integral part of the spaceflight story as well. The part of Sally Ride's application, what made her stand out for the folks who were the managers at NASA, was that they looked at her tennis playing and thought, this is someone who knows how to play a team sport. She's coachable, she's physical, she knows how to follow direction. If you ask her to do a set of physical tasks, she is someone who is adept at that. She knows how to get along with teammates. You can talk to her and she'll be able to really participate in that way. And so the importance of her tennis playing was in many ways a real bridge then to her space flight. And you'll see on the screen, we have also in the archival collection found a letter from hers and your.
Do we know what prompted her to become an astronaut?
You know, what was your first name again? Denisha? Okay, that's a good question. Actually, you know, as Valerie sort of said, Sally, what planet are we on?
I've been called that before.
Sally really never had that goal in mind, but what happened to her is, and it's kind of an important double lesson. She was prepared to take advantage of the opportunity. She was basically eating breakfast in her college cafeteria, and she saw the student newspaper, and it said that NASA was looking for women astronauts and wanted them to apply, and it was the first time in history. And so Sally saw that, and then she just had this moment where it was like, you know what, I want to do that. And before that, she was thinking that she would be a university professor and keep doing research and, you know, live the good life on a college campus. So it was really serendipity a little bit, but she was also prepared because she had studied math and science and so on. Okay.
And her astronaut classmates indicated too that once she became an astronaut, she totally embraced it. She worked harder, she worked longer, she was determined to master every skill that was required. But then there came a point in her life after 10 years of doing that when she realized that wasn't the only thing she wanted to do. And I think there's a lesson in that, don't you?
Sure.
That you don't have to stick with the same thing for your whole life.
Follow your heart. Thank you. Good question.
My name is Nicole, and I'm from William. My question is, what was her aspiration in life before she became an astronaut?
What was her aspiration in life before she became an astronaut?
You know what? That's a good question too. I'm just going to jump in, Patty.
Yeah,
but we
go
got to.
ahead. You're going to get to me. Yeah.
Sally thought of herself as a physicist. She had a very important teacher in high school, Dr. Momartz, and that teacher encouraged her interest in science and told her that she should take like one of those. I don't know what you call it. Sally was a high school student, but she took a college class, and that teacher helped her decide to become a physicist, even though Sally had no clue what a physicist was or what they did. Did I answer your question? So I think she was thinking she was going to work at a university, teach, do research, and that would be her life.
I'm going to break in here to make a little remark too. I forgot to mention that Dr. O'Shaughnessy has just written a biography of Sally Ride that tells a lot of stories of her youth. And one of the things I found surprising is that when she was in high school, her friends thought she was an underachiever. Oh. And someone even wrote that in her yearbook, that she was a classic underachiever. But she found herself when she was in her 20s, and that's when she really put her whole heart into it.
Yep.
Okay, let's move on to another question. Do we have an online question? A question from the audience? Okay, we'll come back to Q&A in a minute then. I'm next to talk for just a minute about what I, as a curator, was looking for. I'm the curator for the space shuttle and all the objects related to the astronauts who flew during the period of the space shuttle. And when I came here, we already had Sally Ride's flight suit and had it on display for quite some time. But I was interested in what else we might find from her career as an astronaut and what we might find that from her earlier life that gave some insight into how she ended up becoming an astronaut. So two of the objects that I was particularly pleased to find were this telescope, which, as you can see, is a child-size starter kit for a telescope that her parents had given her when she was quite young, because she was already curious about nature. She was curious about the sky, the constellations. She just wanted to learn everything there was to learn. And so they gave her and her sister to share a telescope and also a microscope. And so we selected both of those. And her sister, who's about 2 years younger, remembers very clearly that they used to take the telescope out at night into the front yard and look at the stars and the planets and speculate about what might be out there. So that was good to find. We also found slide rules that she had used when she was a physics major in university classes. The helmet I was also delighted to find, because while we had a flight suit for space flight, we didn't have anything really to indicate her love of aviation. All astronauts learn to fly in the T-38 jet trainer. Only the pilot astronauts get to sit in the front seat, but the scientist astronauts sit right behind them, and they serve as navigators, and they learn the whole process of navigation. And they wear NASA-issued flight suits for that. But apparently they can choose their own helmet, and so this was Sally's helmet. And I loved it in particular because it's color coordinated to her flight suit, and it has her name in a flourishing script on the back, just above the neck. And to me, this was, and I may be completely off base, it may not have been in her mind at all, but to me, this at least suggested that something kind of stereotypically feminine was in her character too, that she wanted to match. And she just didn't want her name scribbled on her helmet. She wanted it to look nice. look pretty. And so we collected these. I also collected some of her badges from her years at NASA, including her visitor badge from when she went to NASA to interview to be an astronaut, and her astronaut badge. And then Tam took us at the end of our visit into one more room that had a trunk in it. And this is another instance of Sally curating her own life. In that trunk, she had put everything that was really special to her that she wanted to be sure was kept. And that's where the astronaut clothing and the helmet were. That's where the badges were. That's where some special awards and medals and medallions were. And that's where a lot of worn t-shirts were. And I don't mean new t-shirts still in plastic wrap. I mean t-shirts that had sweat stains, and they were faded, they were wrinkled, they had been laundered, but they were all linked to her flights or to the fact that she was a female astronaut. And one of them said, "A woman's place is now in space." And one of them said, "Well, yes, I am Sally Ride's father." And one of them had an enlargement of the logo for her first mission, which subtly had designed into it the symbols for male and female. So there were 4 male symbols and 1 female. So these were all things that she cared about and used, and so I selected a number of those. And I think that indicated to me that we all curate our own lives to a certain extent by what we choose to keep and where we choose to keep it. And Margaret was the first to articulate that among us. But then I realized that's not uncommon. I think we all do that. And then,
well, I'm going to jump in and tell one bad story on you, which is that the curator also has to make very hard choices, because one of the other things that was in that trunk is a flight suit that is very similar, not the same, Valerie would point out, as the one that we already have on display at the museum. And Valerie very badly wanted a second flight suit. And we said, you know, when we come back to the museum, they're going to say, "We have a flight suit. Why do you need a second one?" And Patty and I kind of collectively talked Valerie down from, you can't have everything. You cannot have everything, and you have to make some choices. And we kind of kept, on our way to the airport, kept thinking Valerie's going to turn the car and like go flying back to that trunk, because she desperately wants the next flight suit that's slightly different. It did have slightly different patches, but we said, you know, when we come back to the museum, they're going to ask hard questions about why did you get a second flight suit when we very clearly, you know, we have one. You know, the museum has one. So sometimes even sometimes the sorting is easier, and then sometimes you're making very hard choices to leave behind things that are kept in very good hands, but that you'd love to have in the National Collection, and you have to make some hard choices.
You did let me take a flight jacket, though.
The flight jacket is a completely different garment.
Right. Okay, Patty, let's talk about papers, because that's a whole different universe.
Yes, it is. And as we've been talking here about the artifacts, and I think when people think about museums, they immediately think, oh, of course, artifacts. But the museum has a very, very fine collection of papers dealing with aviation and space history. In fact, we have over 17,000 linear feet of papers. And historically, they've always kind of dealt with the technological advances that was happening in the aviation and space field. But I've actually been the acquisition archivist now for 26 years, and I've always been very keen to collect the papers of the people behind those technological advances, because I really think that's an important part of the history. And that's especially the case when it comes to collecting papers on women and minorities, because their stories on participating in these technological, mostly male-oriented fields really touches on a lot of social and cultural aspects that make aviation and space history that much richer. And so I was absolutely delighted when Tam reached out to us and said that she had this material. And when I went out there, I was looking for, and I was excited about it for 2 reasons. Number one, just I knew our researchers in general would be very interested in just the general space aviation material that was in it, but then to take into account Sally's iconic role as the first American woman in space, would be just a wonderful resource for our researchers and for our staff. And it would also help complement the artifacts that Valerie and Margaret were picking out. So I went out there and I was looking not only to collect material dealing with her space accomplishments, but just like Valerie and Margaret, I was looking to try to put those space accomplishments as much as possible into the context of her entire life and her professional career. And so I was going to go out there looking for material that happened before she was selected as an astronaut, and then, of course, the period she was an astronaut, and then that large segment afterwards when she was doing, she was being a scientist and a professor and an advocate for STEM education. And so I ended up taking 24 linear feet of material. Basically, I took everything Tam would let me take from the house, and I have to say that you said Sally was a hoarder. I've been doing this for 26 years. I have been in hoarder houses. Your house was great. And Sally was very organized. Again, she very much curated her material. Almost everything I ran across, I said, wow, that really puts this aspect of her career in a sharp contrast to other parts. So I thought it was all very useful. And what I'd like to do with my segment is I'd like to show you some examples of some of the material that I selected. And I'd like to start with material that I think most people would say, oh, of course you collected this material because it's dealing with her astronaut career. And so what was just on the screen was the checklist for the Canadian arm that she did on her first flight, STS-7. And if we go to the next slide, we can see these this is an example of one of the training manuals she had. We collected about 2 linear feet of material just dealing with her astronaut training and her manuals. You can see on the sketch here the Canadian arm coming out the top. That was one of Sally's tasks that she was to do. She was the first woman to do it in space, and that helped her retrieve a satellite. And you can see also what I love about her training materials is that she has marked up, she's highlighted just like you would for any class that you were trying to make sure you passed the exam. Highlighted things, and she also annotated things along the way. So that'll be really useful for our researchers who are interested in understanding the training that the Space Shuttle astronauts were going through. And I'd like to segue from there into a couple of things, talking about Sally's iconic role as being the first American in space. It was first American woman in space. It was a really big deal on both kind of the public arena and also on a private level. So if we can go to the cartoon. Here's a cartoon from the Minneapolis Star-Tribune. And this is really kind of touching on, and this was something that Sally evidently had carefully cut out and saved, talking about the stereotyping she had to deal with becoming the first woman astronaut in space. And I just think it's very indicative on the kind of things that were happening on the public area on a larger scale. But if we go to and show something on a more intimate scale, this is a letter that she got from somebody she didn't know, Linda Halpern, and Linda contacted Sally and sent her a copy of this letter that is being shown on the screen. Linda, when she was a girl in 1962, sent a letter to President Kennedy asking how she could become a woman astronaut. And President Kennedy sent it over to NASA, who wrote her back and said, you know, thank you very much, but women aren't astronauts because you don't have the training and you're not physically able to do it. And Linda had actually saved this all these years, sent a copy of this along with a letter to Sally saying, for me, this is such an exciting thing that you're finally breaking this barrier for all of us that were denied that opportunity. So I really love this example. And there's lots of examples of this, from senators to famous people to people who aren't famous at all, like this woman who grew up to be she's a tort lawyer, but it really made an impression on her. So from there, I'd like to talk about, after she flew, she continued to play very important roles in NASA, as Margaret talked about. She was the main author led the RIDE report, which was about kind of strategically where NASA should go. But she also sat on several commissions that were very important. This is one of her notebooks. She was on the Rogers Commission, which was for the dealing with the disaster, the Challenger accident. And she was the only astronaut that was asked to be on this. And this is the outside of her notebook. And if we can go to the next slide, we can show these are actually the notes that she wrote as she was going through these. And these are fascinating and going to just be very interesting for our researchers that were going through what the problems were with that flight when it exploded, and what the commission members, specifically Sally, were thinking about how to get NASA back on track. For example, these pages are kind of showing the problems with they didn't have enough parts, they didn't have enough time, basically they didn't have enough resources, so a major problem that NASA was having. So that's kind of the things that people would expect us to have. But I also collected, if we can go to her physics, I don't know how well you can see this, she did keep all her physics homework, which is like amazing. Now, I can't tell you what this says or means because I'm a historian, but the fact that she kept it and was so interested in it, I think really speaks. So I took them all. I took probably a box of her undergraduate work. She had a undergraduate degree in both physics and English. And you can see how that just really, being a physicist was very important to her. Not only did she keep all those, it shows how interested she was in science. And I also collected material dealing with what happened. I'm sorry, you can go back to the other one. I wanted to show how it kind of continued on. This is after she left NASA, she went back, she was a professor at University of California at San Diego, and she published over 40 papers, mostly based on her physics research. So she was an incredible physicist. And the other one that you can go to now is her English homework, which I love because the professor wrote on this, I hope you're as good as physics as you are in literature, which you're very fine indeed. And yes, she was. And I think one reason I collected her homework from college is it really shows how she was setting herself up to be an excellent scientist and a great communicator, which is what her English degree brought her. And that's why she was so sought after, I think, on commissions. She was a person of integrity, but she could understand the science and she could communicate it with others, and that's what made her so very successful at that. And then the last thing I'm going to do is I have to show my favorite picture that I found, which is a mocked up picture of Sally reading a childhood book, and somebody had done a thought bubble, and those are some of the controls that would have been in her on the space shuttle. And this was actually, I didn't see this the first time around until I got back. This was actually in that first manual I showed you on the first page, so she took that up into space with her to remind her.
That is a great segue. The picture of Sally with a book is a great segue back to Tam, to let Tam talk for a couple of minutes, if you'd like, about the process of writing your new book, a very personal biography of Sally by the person who knew her best in the world. Would you like to share with us a little bit about what is it like to be a biographer?
You know, is it really, I thought about writing a children's book about Sally for a lot of different reasons. And I started working on it 6 months after Sally died, and it was simultaneously torture to be thinking about her, looking through photographs and so on, but it was also very comforting and a good process for me. And you know, what I really cared about was writing a book that told the story, kind of the true story about Sally, who she was, what she was really like, what she cared about. And at least some of the very cool things that she accomplished. You know, of course, being the first American woman to fly in space, but all the other stuff too, that, you know, she was a person, she didn't cash in on her celebrity. She worked, you know, and she dived into the things that interested her and worked really hard. And I think that's an important story for boys and girls, you know, across our country to know. And the other thing is that, you know, this is a very personal book, and but the other thing that I think is so important is that there are very few biographies, especially about American heroes, who are gay or bisexual or whatever whatever the right little box is. So I just thought it was important to tell the true story, and young people are very savvy, and young people, even in upper elementary school, are they're smart, and they see what's going on in the world, and they have opinions, and I think young people, maybe even more than us older folks, kind of respect individuality and people's decisions. Anyway, I just thought it was an important story to get right and to be honest about. And what I really hope is that, the young people who happen to read the book, kind of come away and go, wow, what a fun and full life Sally Ride had. And then the other thing I kind of hope that they come away with is sort of like, love is love, no matter the gender of the couple. Love is the bottom line. So, and I was very fortunate because Sally did save so many, I had just this treasure of photographs. And so, I'm lucky, I worked hard on the writing, and I actually did the writing first. And then I had gone through all the photographs, so I kind of knew which ones would fit in the various places. But I wrote the story first and then added the photographs. But the photographs are just amazing, and just help tell the story of her life.
And we have that book here today, and immediately after this program, Tam will be going to our shop and we'll be signing books there. So if anyone's interested, you can chat with her for a few minutes, talk about the book, and have a little one-on-one time to ask some other questions. But before we close out the program, I'd love to hear a few more questions from our audience, and I see we have a couple lined up, so go ahead, please.
My name is Nia, and I'm from Whittier. And my question is, what is Sally's favorite subject and why?
What was her favorite subject?
Do you want to answer
Sure.
that? What was her favorite
What's
subject?
your favorite subject?
I like reading.
You like reading? Yeah. Okay, actually Sally loved to read. And so she loved to read all sorts of books. And I think, probably starting in middle school, science became kind of rose on the list and became her favorite subject. And then by the time she got to the end of high school and college, it became physics. Who knows what physics is? No, it's the law. It's the way the universe works. It's the fundamental forces and force is probably the way to say it. Forces and particles that determine everything. And she was just fascinated to know that. And she also was a little bit, she liked that physics was hard, so that she could say, I'm a physicist. I learned that hard stuff. I'm pretty cool. Thank you for your question.
Let's take an online question, which is, what was the most surprising thing you learned about Sally Ride doing your research?
We did that one.
I think we did that one, but I actually I know what we found when we got to the house to work through things. I would be kind of curious to know, to you, going through the process of re-examining all of these things and trying to write the biography, what's the most surprising thing that you learned during your research?
That is a hard question. It wasn't a surprise, but it was kind of a wonderful reminder. And actually, the 1-minute video of Sally, you see it in there, and it was like Sally enjoyed her life. She had fun. She was smiling in almost every shot during the video. She was having fun with her teammates. She was having fun being in space. And you kind of imagine a person being very serious or maybe scared or all sorts of things. And she was absolutely in the moment having fun. And that was really Sally. So I, looking back and talking to her mother and her sister and having them, retell the family stories and the trip to Europe and various things, Sally had a really good life. And the reason she had a good life, she was blessed with a very solid, stable family, but she was also really blessed with the ability to live in the present moment. When you were with Sally, she was with you. She wasn't distracted, she wasn't looking back, she wasn't looking forward. And she had a very fun and fulfilling life. So yeah, it was kind of that reminder that, she had fun. She was a happy kid. She was a happy teenager. She was a happy astronaut. It's just kind of cool.
And apropos of that, when she landed after her first mission, she said, I think that's the most fun I will ever have in my life. So, yes, do you have a question?
My name is Kasir Pervez, and I'm from Whittier Education Campus. And my question is that, how does her athletic ability help her to be an astronaut?
How does her athletic ability help her to be an astronaut?
Good question. Good question.
And Margaret addressed that a minute ago, but you're an athlete too. Maybe you could comment on some of the characteristics.
I actually think it's two things. Especially at that time, it's sort of the uniqueness it makes you stand out if you apply for a job or even apply to go to college. If you have something else, that you're on a soccer team or you play volleyball or you play tennis, it makes you stand out. Okay. And so that helped Sally, and that's what Margaret was referring to when Sally applied to become an astronaut in 1977. But the other thing is playing sports and having to work with coaches and teachers and teammates, and also being in competition. You don't win all the time. You lose, and you got to learn to cope with that. And that's my mic, sorry. And so there's lots of really cool lessons you learn from sports or playing a musical instrument or any of the other extracurricular things that you love. They help you with all aspects of life. So, and Sally, as part of our company, this is beyond your question, but I go off. But Sally would, as part of our company, would give talks around the country. And many times parents or teachers would say, I've got this smart kid, boy or girl, and but the trouble is, the trouble with my daughter or son is that they like football or they want to play the clarinet. And Sally would say, so what? Let them do it. To be a scientist or to be anything, you don't have to just do one thing. Because if you follow the things you enjoy doing, they help, everything kind of reinforces everything else.
Sure.
Anyway, sorry for a 48-hour-long question and answer.
If I could comment on the photograph we had with the 4 girls lined up at the net on the tennis court, the one that is second from the left is Tam O'Shaughnessy, and the one on the right side is Sally Ride. And you were both about 14 then, competing against each other.
Yes.
And if I recall the story, you were actually the better player. You played pro for a while.
I would say that, and Sally can't deny it. She can't change the story.
Oh, well, I think
I think we might have one left.
I'm Charlotte York from Atlanta, Georgia. And my question is, men and women were traditionally kept separate, like in the military, and here she is, a woman in space with all these men. And I just wonder how that was for her. How did they treat her as a woman? That's my question.
Yeah. So,
I think they treated her as one of the guys, and she considered herself one of the guys. She used that phrase, and Margaret can back me up on this, I think. Those first 6 women that were selected into the astronaut corps did not want any concessions made to them because of their sex. The only thing they asked for was a separate restroom and shower in the gym at Johnson Space Center. But other than that, you're on a crew, you're all there to accomplish your mission. You all carry the same load, and you're part of a team. And by the time they actually flew in space, they had been sharing an office together for more than a year. They had been on wilderness survival training together. They were essentially a family. It was like, in a way, it was hard work, but it was also like going camping with your best friends. So she never reported any discomfort. I think she did suggest that they add a privacy curtain to the toilet compartment, which is literally a little closet almost, and it was awkward to close the door. So she suggested a curtain, and they all benefited from that.
I think NASA worried a lot before women joined the astronaut corps about how would this work in such a small space. And part of the reason it worked is that those first 6 women, Sally Ride and the others who were in that class from 1978, were so good at what they did. I mean, they were just deeply competent. You know, if they were given a task, they learned every part of the task. And that was in a group of 35 new shuttle astronauts who were all deeply competent, you know, get that job without working very hard. And so I think they proved themselves equal to that. And then by the time they went into space, they weren't thinking about, oh, this is the one woman, or this. They were a group with a task, and they were all very interested in doing it well.
Yeah, I would say that I think the astronauts felt that way. I think the public was who had the difficulty kind of with that. And you get the kind of sense of frustration if you see Sally in any of her interviews when, you know, they're asking, you know, do you cry when you get upset? And she's like, I bet you don't ask the guys that question. And, you know, so I think that was very frustrating for her. But within the crew themselves, they were also such competent professionals. I don't think they saw it at all. I mean, it was just, you know, a crew together. So
right. Yeah. There were folks who had roses for her when she landed,
yes.
And she did not take them. But there were not roses for the whole crew, so she was not interested in being singled out in that way. You know, some sort of Miss America moment.
Right.
And I think for a person who never sought celebrity, she did gradually learn how to, and when she needed to be in public, she could adopt that role, but I think it took a toll on her. It exhausted her. Some people are energized by being in the public eye. She needed to retreat from that, and she had a really good sense of how to keep that balance in her life. I would love to keep this conversation going for the rest of the afternoon, but I know that our audiences online and on television and even here probably have some other things they want to accomplish this afternoon, and we're going to whisk Tam off to a book signing. But before we do that, I would like to thank Boeing again for sponsoring this series of programs, What's New in Aerospace. I'd like to thank the students from both schools who came today. Thank you for coming. I hope you're here not just because it got you out of class for a couple of hours, but because you really wanted to come to the museum. And I certainly would like to thank our panelists, Patty Williams, archivist, Margaret Whitekamp, curator, Tam O'Shaughnessy, author, educator, and biographer of Sally Ride. You can tell, I think, that we established a relationship over the last couple of years, and you always do establish a relationship with a donor, but sometimes it's a business relationship. Sometimes it's a much more personal one, and we all really enjoy each other, and we really enjoyed working together, and we're most appreciative that Tam chose the National Air and Space Museum to be the place to go to find objects and papers from Sally Ride's life. If you have friends and family who might be interested in watching this program, it will be on our website, the National Air and Space Museum's website, starting tomorrow. And if you know anybody watching NASA television at home, NASA will be showing it throughout the day today and tomorrow. So spread the word that you now know what historians and archivists do. And I hope you have a much better understanding of Sally Ride's significance, not just as an astronaut, but as a fully dimensioned human being. Thank you for being here.
NASA celebrates LGBTQ+ Pride Month.
For generations, we have dreamed about a place to live and work in space, a space station. And right now, 260 miles above us, that dream is a reality. We dreamed that life up there would benefit life down here. That dream has come true. Can research on board the space station lead to cleaner drinking water on Earth? Can it help farmers produce better crops? Can it inspire a generation of students? Can it even save a life? The answer to these questions is yes. It already has. As the work aboard the International Space Station begins to reach its potential, the benefits to humanity are evident. These are just a few of the stories from people who have realized those benefits in their own words.
Is that 2? You say 2? I found a big lump in the side of my face, and I kept going to doctor after doctor. And I was in so much pain at that time. I was like dying in bed. It hurt so bad. I've never been in so much pain. I went for my first MRI, and then it showed up with like hundreds of tumors all over. And then they sent me to, not Dr. Sutherland, but someone who works in his office. And he thought it was neurofibromatosis, which I have.
We didn't even realize what that was. We'd always heard it called the elephant man disease. There's different types of neurofibromatosis. One of them, the tumors grow on the outside of your skin. The other one, the tumors grow on the inside, and hers grow on the inside.
A long time ago, when we were thinking about this, we approached McDonald Detweiler Associates. It's a company that happens to be located in Canada that built robots for space. They built what Canadians call Canadarm, and then they constructed the special purpose dexterous manipulator for the International Space Station. And the idea was, if they could build such complex robots, perhaps in collaboration with medicine, we could build a robot that could operate inside an MRI machine.
We did not realize that it was built out of the same material as the space arm, and we're quite amazed that that's what he had made it out of.
But it's the multi-dexterity of the robot, and that robot could perform tasks that made us become increasingly confident that we could overcome the challenges related to building a robot that could operate inside an MR machine with the precision, the accuracy, and the dexterity of a neurosurgeon. It just so happened that the first individual was a young woman, and the young woman harbored a fairly complex tumor underneath the front part of her brain. A machine like NeuroArm can manipulate tools at an accuracy of 50 microns. that is overwhelmingly superior to what the best surgeon might be able to do.
I think it's fabulous. To me, it's actually mind-boggling that someone can take that material and put it into a life-saving device that can help millions of people.
I honestly think that right now I'd be bedridden. I would not be able to get out of bed if it was not for my doctors. My parents would be taking care of my kid right now. I guess I'm glad that it hopefully helped people who have my disease, and I hope that it helps people who need surgery in the future. If they're ever propositioned with a chance in the future to have something done like this, I hope they take it.
Estamos en la comunidad Tres Picos.
We're in the town of Tres Picos.
Es una purificadora de agua que utiliza.
This is a water purifier that uses technology developed by NASA and makes free purified water available to all of the people of the community.
La tecnología fue desarrollada para
The
la
technology
Estación Espacial Internacional.
was developed by NASA for the International Space Station.
En el caso de esta comunidad viene de la red.
In this community, the water comes from the town. But in other communities, where we are working in Chiapas, it comes from the wells, from rivers, from streams, from springs. The water can come from practically any source that you can imagine. People who drink contaminated water alter their health. Their children's development is diminished.
Yo me llamo Raquel Pérez Pérez y soy asistente.
My name is Raquel Pérez Pérez, and I am the campus assistant of this school.
Infección de la panza.
There were lots of children with parasites and stomach bugs before the purified water came. Now the kids are healthier because they now drink purified water from the plant. The energy that is being used is solar, and the children come to recess with their cups and they get the water themselves. They are happy now and they want to come and drink water all the time.
When you get involved with a plant of this kind that gives people access to pure water for human consumption, that is going to prevent people from getting sick. What you're really doing is improving people's health, but also you're improving the economy for these people. If we could put one of these plants in every community and have people use it, you would have resolved one of the most important sources of health problems, at least in the rural areas of Mexico. That's the truth.
Bien usado cambia la vida de una comunidad. La cambia la
If it is well used, it can change the lives of an entire community. It gives you children that learn more. It gives you parents who spend less money on medicine. It changes the future.
Our farm is called AWG Farms, started back in 1975. It's a family-run farm. I have two brothers now, and my son-in-law is in the operation. This will be a third-generation farm in this particular area. The main crop is sugar beets. Then we have spring wheat, sunflowers, soybeans, corn, and once in a while we'll raise some edible beans. Remote sensing is a way to look at our crops during the growing season to be able to determine if we need to do any monitoring of disease and or fertility differences. There was an organization over in Grand Forks, North Dakota called UMAC. That organization put a camera on the space station called Isaac. Well, the biggest problem with satellite imagery is the fact that Landsat we get every 16 days. And on that 16th day in this region, if we have cloud cover, that image is virtually useless for us. So then we have to wait another 16 days. The biggest thing with Isaac, we would get much more often. When we wanted to get that particular image, Isaac gave it to us when we wanted it versus a more rotational type satellite. And they were able to get imagery to us with a couple bands of light, the more necessary ones that we needed, which is near infrared and red. The near infrared band is something to do with biomass, how the crop is growing. More biomass, usually more yield potential. We're able to obtain a piece of software that's written by a local programmer in this region that allows us to take these images and manipulate them into zones within the field itself. And by doing that, we can see different patterns in the field. And within those patterns, we can manage the field differently based off of biomass or reflectance of the field itself. It's just a tool that we can use as a reference to be able to make better decisions. And by doing that, our farm is more profitable. And that to me is very important.
I grew up out in the country in Indiana. Corn and soybeans were the main crops. I had always been interested in technology and in science. Being out in the rural setting, there wasn't a whole lot of support for this. Space Jam is an annual weekend Boy Scout event, and we do all kinds of technology-based things. We have about 1,000 people that come every year. This is our 7th year doing it, and it's a blast every year. The contact with the International Space Station was one of the driving forces that helped to create Space Jam. In fact, the first Space Jam was really basically only about the contact.
It was a dream of the ham radio operator to say, hey, I want to talk to the astronauts on the space station. How cool could that be? That's the top of the game.
Each year we call up the International Space Station and we give these young kids the opportunity to ask questions to the astronaut.
Is it true that it will take over a year to get to Mars and back over?
It absolutely is true.
The first time that I remember really having this real impression was, I think the 3rd year we did this. I was in charge of actually calling up the space station and establishing the contact. We were out in the middle of the night in a field, and I said, NA1SS, NA1SS, this is WB9SA, calling for a scheduled contact. Do you copy, over? And I said it again, and all of a sudden, real crisp comes back, WB9SA, this is the International Space Station, how are you doing tonight? And we're like, oh, this is amazing. I graduated as valedictorian, and I was lucky enough to be admitted to Princeton with a complete scholarship, and I then moved to San Francisco, where I'm a software engineer. So I went from living on a farm to living downtown in San Francisco, writing software for people. It was a really amazing experience to do all that.
Minas Gerais é estado.
Minas Gerais is a large state. Our territory is about the size of France, and we consist of 853 units and municipalities. There are large distances between our communities and many very isolated rural communities.
Nós estamos utilizando nova tecnologia.
We are using new technology that impacts the quality of prenatal care and the diagnostic capacity of the primary care doctor in these situations involving distant, isolated communities.
Providing medical care for people in remote locations, like distant rural communities or the International Space Station, can be difficult, because trained medical personnel are not always available. NASA research teams develop techniques that enable astronauts aboard the space station with minimal training to operate an ultrasound device using simple printed guides. The ultrasound images are transmitted in real time to a doctor back on Earth. who can make medical decisions without actually being aboard the station. These same techniques have been adapted for use with portable ultrasound devices in communities where expert medical care is not always available.
Bom, meu nome é Joaquim Edevilson Diniz.
My name is Joaquim Diniz. I'm a doctor in the town of Manga.
Manga, a gente vive uma parte.
In Manga, people live with a particularity, and that is isolation.
Nós temos uma barreira geográfica que é o Rio São Francisco.
We have a geographical barrier that is the São Francisco River, which is both a blessing for the region, but it also isolates us.
Direita do Rio São Francisco. Nós vivemos numa região em que os
We live in a region where financial resources are few. People do not have a lot of work, but they are honest, good people who do not have much opportunity. So there are many needy people who need these resources and rely only on this institution to provide assistance.
E uma tecnologia dessa que vem.
This is a technology that helps us solve many problems.
Que teve caso de uma paciente que estava com insuficiência respiratória grave.
That was the case of a patient who came to the hospital with severe respiratory failure, and the people realized she would die in just 20 to 30 minutes. We talked with Dr. Parzelli, who was training us to use the ultrasound. He came and applied the ultrasound and discovered large amounts of fluid around her lungs and heart. We performed the procedure and drained a lot of fluids. In 10 minutes, the woman immediately experienced an improvement and in half an hour was already walking. It was like a miracle, a rise and walk. She was dying in front of us without people knowing what was happening. This ultrasound was instrumental in saving the life of that patient.
We've only begun to see the International Space Station's benefits to humanity. These are just a few of the ways that the science and research conducted aboard the ISS is improving lives today. There are countless more benefits to come, sometimes in ways that we have never predicted. Every day, hundreds of scientists around the world are working with the crews on board the International Space Station to perform life-changing research. Every day, they use the weightless environment of space to conduct experiments in ways that can't be done here on Earth. And every day, those experiments improve life for people all over the world. This will be the legacy of the International Space Station's benefits for humanity.
From space, we see deep into the heart and veins of our ever-changing planet. Pictures of Earth are worth more than 1,000 words. They are the blueprint for our future. To unlock the full potential of space's unique vantage point, we've created powerful tools. Tools that gather valuable data. Data that enables farmers to efficiently manage water and fertilizer for stronger food yields. Data that scientists use to monitor ticks and mosquitoes that carry harmful diseases. Data that first responders use to find the fastest routes to save lives. That's only a glimpse of what we can do today. In the future, when combined with AI and powerful computing, a broader range of space data would generate infinite solutions for Canadians. Imagine a future where we can use space data to better understand and predict the impacts of climate change, like rising sea levels, extreme weather, wildfire risk, and flooding. Measure the health of our forests and create predictive maps of pest damage and burn extent. Produce real-time dynamic navigation routes to protect whales and other endangered species. Ensure security and sovereignty in Canada's vast Arctic. Tomorrow's challenges require investing in innovative solutions today. Earth observation is key to securing economic opportunities and improving the lives of Canadians. Together, we can define Canada's future.
This is a science mission on par with Apollo missions, Space Shuttle, International Space Station, and Hubble missions. For nearly 2 decades, thousands of people around the world, many spending their entire careers, built the James Webb Space Telescope. And it all comes down to this.
Once we launch the James Webb Space Telescope, there are no second chances. We have 300 single-point failure items, and they all have to work right. When you're 1 million miles away from the Earth, you can't send someone to fix it.
We've never put a telescope this large in space. We want to see distant parts of the universe humans have never seen before. Looking back in time almost 14 billion years to see the first galaxies that formed after the Big Bang. And we want to search for the building blocks of life in the atmospheres of planets orbiting distant stars. To unfold the history of the universe, we must first unfold this telescope.
This is the largest primary mirror, the largest sun shield, and the most powerful space telescope ever built. And yet, this large telescope needs to fit inside a 5.4 meter diameter rocket fairing. That's the largest fairing size available on any rocket, and it's the fairing size on our ride to space. The Ariane 5, provided by the European Space Agency, is one of the world's most powerful rockets. To cheat the fairing size limit, we built Webb to fold, like origami, to fit inside the rocket fairing. And this brings us to our most challenging part of this mission, unfolding it in space.
10, 5, 4. Think of what you're doing. You're taking this extraordinarily delicate, precise, state-of-the-art scientific instrument, you're slapping it on a rocket, and for the next 8 minutes, the explosion from that rocket is following you into outer space. Vibrating you, shaking you. Everything that goes into outer space has to live through this environment and work once it gets there without having someone come to fix it.
Two weeks. That's how long it will take to fully deploy the Webb telescope. We can take longer if we need to, but those 2 weeks after launch are going to be nail biters. This is the Mission Operations Center at the Space Telescope Science Institute in Baltimore. Those 2 weeks after launch will be like our Super Bowl, World Cup, you pick the analogy. Years of training comes down to these moments.
The Webb Observatory has 50 major deployments, 50 depending on how you categorize them, and 178 release mechanisms must work to deploy those 50 parts. Every single one of them must work. Unfolding Webb is hands down the most complicated spacecraft activity we've ever done. Then again, nothing about Webb is easy. We've never done any of this before. There's nothing simple about sending anything into space. You can't do it without taking risks.
This mission is squarely in new spacecraft territory. Webb is the perfect example of science desire driving engineering capability to new frontiers. Webb's unique design was born from reasoned engineering to accomplish its science goals.
Here's the plan. Shortly after launch, we unfold Webb's solar panel for power and our high-gain antenna for communication. About 12 hours later, we have an important engine firing that sends Webb on the proper course towards its orbital destination, about 1 million miles away. That's where Webb will do its science. Webb will be moving so fast, it passes the moon's orbit in 1.5 days, half the time it took Apollo astronauts to reach lunar orbit. First, we lower the sunshield pallet, then raise Webb's primary mirror and instruments away from the sunshield. The solar wind will push us around with the sunshield open, so we'll unfold a trim tab to help keep us stable.
We got these huge, iconic, golden segmented mirrors that will help us deliver amazing new images from the cosmos. But in some ways, the sunshield is a lot more complicated, and it's just as essential. Without it, nothing works.
Here we've got 5 sunshield layers, or approximately 8,900 square feet, almost the size of 3 tennis courts, a very thin Kapton material, about 1 to 2/1000ths of an inch thick. Making them go where you want them to go in 0G is extremely challenging.
The sunshield shades the telescope from the heat of the sun, earth, and moon. The concept is simple, but there is nothing simple about the design or operation, especially when you get to space. Webb's sunshield assembly includes 140 release mechanisms, approximately 70 hinge assemblies, 8 deployment motors, bearings, springs, gears, about 400 pulleys, and 90 cables totaling 1,312 feet. All this just to keep the sunshield under control as it unfolds. First, we release these special restraints that protect the sunshield during launch. They roll out of the way, but not all the way until we are ready to deploy aside. Next, we release a set of covers over the core region. Now comes the critical point. All 107 sunshield release mechanisms need to fire on cue. 107. They free the 5 sunshield layers, allowing them to extend as the mid-booms deploy.
Sunshield fully deployed, we start setting up the optics. First, the secondary mirror is extended and locked into place, and a special radiator behind Webb is extended, which helps further lower the temperature of the science instruments. Finally, we open the primary mirror's wings and lock them in place. With that done, Webb is in its final configuration, but we're not done yet.
After 47 deployments, and accomplishing the hardest spacecraft unfolding NASA has ever done, Webb still won't be ready for science.
While the instruments cool, we'll control motors behind each of Webb's 18 mirror segments, a secondary mirror, and the fine steering mirror located inside the center of the primary mirror. We'll precisely align the mirror segments to form a perfect mirror. Then, Webb will be ready to explore the cosmos.
NASA celebrates LGBTQ+ Pride Month.
NASA 1, we have an ejection. The aircraft is descending over the North Base area. I have a chute. The pilot's out of the seat and the chute is good. Okay, Bravo, copy.
We had a highly competent team, very experienced, many flights under their belt. We had a number of pilots that flew the airplane. The pilot in particular that was flying that day had been on the program from the very beginning, highly experienced with the X-31.
Each mishap has its own set of circumstances and its own sequence of events. But you find similar issues: communications, complacency, assumptions that haven't been warranted, human frailties. And you have to account for these things in a program.
This is like a chain. You make a chain when you have any of these accidents, a chain of events. Any link of the chain, if it were broken, you would not have an accident.
This was the A-team. We had the best people from every discipline, from every organization, and we lost an airplane. So if it can happen to the best team, it can happen to any team.
The X-31 research effort began in the late 1980s as an international program involving DARPA, the U.S. Navy, Deutsche Aerospace, the German Federal Ministry of Defense, and Rockwell International. The program's goal was to explore the tactical utility of a thrust-vectored aircraft with advanced flight control systems, using an aircraft designed and built specifically for that task.
The X-31 was a real pioneering program. And in fact, the X-31 program pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HARV.
The initial X-31 flight tests were conducted at Rockwell's facility in Palmdale, California. But in 1992, NASA and the U.S. Air Force joined the X-31 research team, and the test flight program was moved to the Dryden Flight Research Center on Edwards Air Force Base. And before too long, the X-31 was turning in some extremely impressive results. By any measure, the X-31 was a highly successful program. It regularly flew several flights a day, accumulating over 550 flights during the course of the program, with a superlative safety record. And yet, on the 19th of January 1995, on the very last scheduled flight of the X-31's ship number 1, disaster struck.
This particular flight had been on the books for some time to get done, and it was, by our standards, an absolutely routine flight.
We were not expanding the envelope. We were not trying anything new. We were flying a new pitot-static tube, but this was in a routine mission, a routine task, routine flight environment with an experienced pilot and experienced crew.
But while the flight was routine, there had been some changes to the configuration of the X-31 since its initial flights. In particular, the original pitot tube, which supplies airspeed information to the plane's flight control computers, had been replaced with another kind of pitot tube known as a keel probe. The keel probe gave more accurate airspeed data at high angles of attack, but it was more vulnerable to icing, especially since the keel probe on the X-31 did not have any pitot heat.
We were never to fly the airplane in ice. That was a prohibited maneuver. So if you're prohibited from flying in ice, you don't need a heater.
Normally, the conditions at Edwards are warm and dry enough that icing or pitot heat isn't a concern. But January 19, 1995 was not a normal day.
The unusual part of the day was we had a high humidity at altitude, actually conducive for freezing conditions. And airplane was operated for in and out of some fairly high moisture content for extended periods of time. Led to some indications in the cockpit and the control room that it was causing problems with the air data system.
This particular airplane had a limit to not fly through clouds, through visible moisture. That day, we were flying very close to and occasionally in and out of very thin cirrus cloud. It didn't particularly worry me because everything seemed to be going along quite normally.
But some minutes, like 5, before the airplane went out of control and the pilot jumped out, the pilot observed that there was some moisture around where he was. So he turned the pitot heat switch on. Now clearly when he turned the pitot heat switch on, he expected that the pitot heat would be working. About 2.5 minutes later, which is 2.5 minutes before the accident, he mentioned that fact to the control room.
Okay, remind me, I just put the pitot heat on. Remind me to put it off. Copy that. Ready?
The pitot heat's not hooked up on a kill probe.
Just stop it. You got enable on? Enable to stop it on.
Mysteriously, to this day, the control room gave him no response. They had an internal discussion as the clock clicked down, and internally it was commented that the pitot heat was not hooked up.
But this vital piece of information was not relayed to the pilot for more than 2 minutes. And even when it was, the information was not stated as clearly or strongly as it could have been.
And pitot heat. Well, leave it on for a moment. Yeah, we think it may not be hooked up. It may not be hooked up. That's good. I like this.
We had side discussions that should have been going on the intercom so that everybody in the control room was part of the conversation. Instead, we'd pulled our headsets aside so that we could talk to each other because we're sitting adjacent to each other. And that's another part of just control room discipline that we broke down on.
Meanwhile, the first signs of trouble were beginning to appear.
So now the pilot sees an anomaly in his airspeed. He's at 20 degrees angle of attack, and he can see that. And he says to the ground, and I briefed this many times, he said, I'm at 277, I mean 207 knots.
And the airspeed is off, reading 277 knots at 20 AOA. Okay, pitch doublet.
Well, anybody that's been on the program, and lots of people have been on many years, would know that 20 degrees angle of attack is somewhere around 135 knots, 140 knots, doesn't matter. It's not 207 knots.
Apparently, no one in the control room caught the possible significance of that discrepancy. And perhaps even more importantly, neither did the chase pilot, for the simple reason that he couldn't hear any of the pilot's transmissions.
We had a mechanism of hot mic, very important to the pilot in the X-31, that he'd be able to talk to the control room without having to press buttons at certain key times, especially at high angle of attack, which was not going to be a factor in this flight because it was going to go to about 20 degrees angle of attack. But it was a general operating procedure that was compounded because our hot mic system didn't work always very well. And when it didn't work, it put a lot of static in the earphones of the chase pilot who wanted to hear the hot mic to know what's going on.
So it was the one-sided nature of the communication that kept me from having the situational awareness to be able to step in and say, hey, I'm reading X knots and you guys are reading Y knots, and these two numbers should be the same, and they're not.
The X-31 did indeed have an air data problem. The unheated keel probe had frozen over in the cool, moist conditions, causing it to start giving incorrect airspeed information to the X-31's flight control computers.
in terms of the accepted risk, the failure of the pedostatic system or damage to it was well known. It was well understood. The pilot himself had simulated the failure in simulations before we even got the airplane. And it probably helped him understand that he had to get out of the airplane because the time is short when the airplane is diverging.
And we went through quite a thorough review of the hazards that we knew or could come up with based upon the design of the flight control system. And we thought we had a good handle on that. We thought we could lose the whole nose boom. We could take a bird strike, wipe out the whole nose boom, and fly home safe. As a result of that, we thought we had a pretty robust system.
The reason the team thought they had a robust system was the X-31's flight control system was designed with 3 backup reversionary modes the pilot could select in the event of an air data problem or other systems failures.
So in the case of if you saw something that was not right or the control room saw something that was not right with respect to the airspeed system, they could tell the pilot to go to R3.
R3 was a reversionary mode that would have removed within 2 seconds the airspeed data inputs into the flight control system. The control surface response to pilot inputs would then be independent of airspeed, allowing the airplane to remain controllable for the remainder of the flight back to the landing.
The accepted risk was probably reasonable, but here's the kicker. The consequences of a failure are so high here that you really needed to put some special attention on this. The designer did by putting R3 in.
But nobody on the test team, including the pilot, realized that the X-31 was experiencing an air data problem that would require implementing the R3 reversionary system.
For several minutes, we had indications that the airspeed was becoming poor, both in the cockpit and the control room. In our last-ditch catch, nobody stood up and yelled, "Wait a minute, this can't be right."
Because had we realized what was going on, the control system had the ability to go to fixed flight control gains, and with fixed flight control gains, it would not have been a problem. They would have been able to land the airplane safely. But we just never got enough information to make the decision to do that.
We had an alternate airspeed indicator that used a different pitot tube, which would be less susceptible to icing than this special tube. It was at the pilot's right-hand knee, and he never looked at it. We had a lack of attention to the reversionary modes. Gradually, we were not thinking. We learned to depend on the control room. They're going to tell us when we need to go to R2 or R1 or R3. We need to know as pilots, which we kind of forgot, where are the safety nets? The safety nets push the right button, didn't get the test data, but you bring the aircraft back. So if you didn't understand what was happening, we should have been constantly reminded, push the button and talk about it.
Pilot obviously wasn't concerned. His experience, probably, if you look at the control room, the pilot and everybody involved in that day's activity, he was the most experienced X-31 in that day's activity. He had been on a program since Palmdale. So he noticed something, but he wasn't concerned, and he didn't ask for help that I was aware of. And so I think the control room said, well, he's not that panicked, I'm not that panicked, and I think that fed off each other a little bit.
The team moved on to the final test point of the day, a simple automatic control response test that required only a command from the pilot to initiate. But once again, the airplane did not respond as expected.
He hits the box, presses the button, and he says, I don't get anything. Well, he didn't get anything because the box was designed not to put any input if you went beyond a certain speed, like 200 knots. So it was seeing the false airspeed of 200 plus knots. And when he pushed the button, it didn't work.
3, 2, 1, go. Doesn't do anything.
But it didn't work because something was wrong. And the control room came back and finally just kind of ignored that and said, it's all okay, RTB now.
It's almost like expecting to hear that went fine. You know, after this program with hundreds of flights and everything going perfectly, in your mind you're hearing things that weren't happening. Everything's fine, worked fine, let's come home.
The normal operation of the system was expected that the system would identify the problems itself, that it would not be the people on the ground identifying an air data problem and calling for fixed gains. Although it was certainly capable of putting that, the expectation would be that the system would do its own self-diagnosis and identify failures.
But the failure we had was a slow failure of the tube, slowly building the ice up. So the changes in the speed were within perfectly reasonable numbers for a real airplane. Software is just not capable of detecting that failure for that system.
There was one or two people that actually knew that there was these little tiny areas that, yeah, it couldn't handle it, but that word never got out. They never stood up and said, oh, boss, that's not quite right. You know, you can handle it over 95 or 99% of the area, but there's really a couple little areas the automated system can't handle it. And that didn't come out till after the accident. I never did get to talk to them about it, but I just kind of felt they didn't want to stop the program, thought it was of no real issue because of the difficulty of getting to such a small area of the envelope.
But as the X-31 began to descend on its return to base, the problems caused by the failure of its air data system became far more pronounced.
We have frozen the pitot tube now, and it's stuck. It's got what it had in it, and it's going to hold that pressure. Now when you start down with a frozen pitot tube, the airspeed, what you see, the false airspeed that he saw, will decrease as he decreases altitude. But we are seeing, the control room is seeing, they have a big display, this big. The pilot is seeing every time he turns his head, he's seeing the airspeed in the HUD. And now it's perhaps at one point, it's at 150 knots. It cannot be at 150 knots. And then it's at 100 knots. And it cannot be at 100 knots. And going on down, it finally, right just before the accident, it gets to 48 knots, which is the minimum it's going to read. But the control system in the airplane is getting this wrong information. And this is a complex closed loop system, and when you put too much gain in, it will start to get unstable and it will start moving the controls, which it did a matter of seconds. And finally, it dramatically pitches up. The pilot, of course, tries to prevent that, and I'm sure the instant that he hit the forward stop and realized he was out of control, he did the natural thing, was eject from the airplane.
We were RTB, return to base, and I started to rejoin on the X-31. As I came up on his right side, about 100 yards away and closing, I saw the airplane start to go into a small wing rock that progressively got larger and larger. And as I got within about 200 feet of him, the airplane pitched up vertical, and approximately the time that I passed to beam him, I saw the pilot eject.
Okay, NASA 1, we have an ejection. We have an ejection. NASA 1, do you read? Yeah, we copy, Dana, we copy. And Sport, NASA 8584 has ejected. The aircraft is descending over the North Base area. I have a chute. Sport, NASA 850, how do you read? 850, say it again, please. Yes, sir. NASA 584 has ejected from his aircraft. The aircraft is descending north of North Base. The pilot is in the chute at this time, descending approximately 1 mile north of North Base.
So there was the knowledge and training in the simulation that taught the pilot when he started seeing the airplane was oscillating, was not controlled, he knew that he had to get out of the airplane very fast or else the airplane would go into a tumble. And he did do that, and that saved his life. I also know that the pilot, as he was ejecting from the airplane, had thoughts of maybe I should have tried a reversionary mode. But at that point, if he would have hesitated any longer, he would have been probably lost with the airplane. So
I did not connect until after the plane departed, While the plane was tumbling, I made the connection. Pitot system had to be frozen, and just didn't come to the realization soon enough to do anything about it in the control room.
Less than 4 minutes after the first comment about pitot heat was recorded between the pilot and the control room, the X-31 crashed just north of Edwards Air Force Base. How could such a routine operation have ended in disaster when flights with far higher risk had been completed safely? And more importantly, what can we learn from the answers to that question?
Every person involved in an experimental flight research program should actually study the mishaps of all experimental aircraft in the past 20 to 30 years. There's a lot of things you can learn because human nature doesn't change, the processes don't change. It's always the same set of contributing factors, just the names and the details change. Of the 10 things, for example, that I describe as causes, contributing causes of the mishap, 6 of them occurred prior to the day of flight. 4 occurred within about 2 minutes. So we had a better chance of working on the 6 than we did on the 4.
In some senses, the X-31 accident started 6 years earlier when the plane was first developed and tested at Rockwell.
We had a hazard analysis from the initial design, and in the accident that had to actually get dusted off. You should never have to dust off one of those. Everybody familiar with the program, all those levels need to have a really good, comfortable feeling of what those hazards are and what is accepted in the risk. There was a redo of that analysis as we moved to NASA in '92, and I think and it was clear after the accident, not everybody really understood what that design was to the detail you needed to understand the full risk of the program. Clearly, from 1990 to 95, you have a large team turnover. We changed locations. We expanded the objectives of the program. And as time rolls on and the new people come in, not everybody has the same understanding or appreciation of the kind of vehicle we're operating. It's a special airplane. It's not the same risk as any other airplane. And to operate it every day, you really ought to have the same appreciation for the risk. And I don't think we as a team did a good job of keeping everybody that came to the program with the same level of understanding of both the design and the risk on the airplane. We shouldn't have had a control room, a pilot, and a team that day that didn't understand that fundamental fact. And it's not elaborate, it's just straightforward. The airspeed I see in the HUD is the airspeed the computer uses. If the airspeed I see has got a problem, the airplane's got a problem. And that fact, it didn't get communicated correctly from old team members to the new team members. And if it had, I don't think there'd have been anybody in that room that wouldn't have yelled stop and jumped off the bridge to make it happen.
There were errors made. The pitot heat circuit breaker was disabled, but there was no placard in the cockpit to say no pitot heat. And notices of the configuration were sent around, but here also we probably lacked one step, and that is to know that everybody got the message. It's one thing to send it out, it's another thing to verify everyone has read and understood it. And so that procedure was changed, by the way, so that people ripped off the bottom of the page and sent it back. I've seen it.
Ironically, the X-31 program also may have been a victim of its own success.
I never saw complacency in this team. I went to tech briefs, crew briefs. It was treated very professionally, and in fact, to some extent, it was treated like an experimental airplane every flight. But certainly you have to think that after hundreds of flights, excellent results, and the fact that none of these hazards, these terrible things that you predict could happen, has ever happened, it could lead you to be less sensitive to things that are happening. Maybe just a little bit of the edge comes off.
Those single point failures were identified, and we made some actual changes to the design of the airplane to account for that. And again, that was in 1989. Why all those were there and what the concerns were and how to mitigate them and how to worry about them we hadn't had any problems with that for 5 years. And I think, again, the complacency just got built into the team. It worked fine. We never had a problem. And those little hairs on the back of your neck weren't geared to stand up when people started having airspeed problems.
Our control rooms used to have a saying on them to prepare for the unexpected and expect to be unprepared. And I think that's a truth in the flight test business that that we need to keep that in mind continuously. I wish that sign was still up there, because that reminder needs to be enforced all the time.
Well, certainly in the case of the X-31, we were returning to base after 2 exhausting days, 7 flights. Ship 1 was now going into the boneyard, or at least it was being retired from the test program. And so we're finally finished. Is everybody paying attention like they should be? Obviously not.
And while the X-31 program flights were highly successful, they did not include an element that might have helped prime the program team to take the one mitigating action that could have brought the X-31 home safely.
We've debated amongst ourselves whether we actually would have been able to convince anybody to use the fixed gain system, because there was not an obvious need for it. The pilot may have been better prepared when things started to go awry to select fixed gains, but I don't know if we ever really would have done it in that situation, because we didn't have a real problem. We did have a real problem, but it hadn't been diagnosed as a real problem.
On a previous program, the X-29 program, we had the same sort of thing. We had an analog reversion mode, a digital reversion mode, and the normal mode of the airplane. We routinely at every test point selected those backup modes, flew them around, so the pilots were much more familiar and much more comfortable with selecting those modes. On the X-31 program, we never selected those modes intentionally. We only used them when we had a sensor failure or the system told us to select those modes.
On the day of the mishap itself, there were additional links added to the chain. There were unusual weather conditions that created an uncommon and unexpected kind of flight hazard. And the team was working with a flawed hot mic system that kept the chase pilot from hearing critical communications from the X-31 pilot.
So, some links in the chain are already built there. Management links. Control room is now talked internally. They've heard some things. They haven't said anything. Some more links are built. We got this chain is building now. The chase pilot didn't hear anything about this, didn't know that he didn't know anything was wrong with the airplane until he saw the airplane pitch up and the pilot jump out. Whereas he could have stopped this anytime.
At any rate, it's a total team concept, and the chase pilot has to be part of that team. The team has to have total communication. So the use of a hot microphone frequency that did not allow the chase pilot to stay up with what was going on with the airplane was essentially keeping me from doing my job, at least at a certain level. And that's one of the things that we changed in the way we do business here at Dryden, is to allow the chase pilots either access to the hot mic or to ensure that all critical communications are transmitted so that all the players are kept up to speed with what's going on. And that was a direct fallout of how the X-31 operation was handled that day.
If one or more of these contributing factors had been caught and addressed prior to January 19th, the chain of events leading up to the accident might have been broken before the flight even took place. Yet there were still opportunities to avoid the mishap, even in the last few minutes of the X-31's flight. So why didn't the team manage to recognize, communicate, and respond to the X-31's pattern of anomalies in time?
So we were seeing inconsistencies between the data from the aircraft system and what we knew of the physics of the problem, that it could not be, that you could not have that airspeed and that angle of attack simultaneously. And for me, I just remember thinking, gosh, I can't wait till we get the data from this flight, because I want to see what's going on. I knew there was an anomaly. We had talked about it between the engineers. We didn't talk about it on the intercom, though. It was sidebar conversations in the control room.
Well, many of us are engineers, and we see an issue. Oh, this is interesting. I wonder what's causing that. And you start thinking about it and trying to figure out what is the answer. In the meantime, the seconds are clicking by. And really, the right response is, something's going on I don't understand. Let's call a halt here and let's just figure it out.
We should have, at the first call of an airspeed failure, puckered up. Whether you're RTB at that point or not, it wouldn't have changed. The kind of failure that was occurring should have triggered a lot of emotion anywhere in the flight envelope.
In the case of any discrepancy, anything that doesn't sound right, feel right, smell right, Let's stop and think it over. And I think that kind of attitude has been built in now into the control room, mission control room processes since then.
We were flying lots of flights. At the peak of the program, there would be days when there would be 5 flight days. I think on that particular day, we were only doing 3 flights. And it was the last flight of the day. It was the last flight for the first airplane. And we had completed all the test points for that mission. In addition, we were going through the RTB, or Return to Base checklist. And at that point, every one of us kind of relaxed. Like I said, what was going through my mind is, I can't wait to get this data. Something funny is going on, and I want to figure it out. And that's another lesson learned, that when we talk about it all the time, the mission's not over till the airplane's on the ground and the engine's shut down. And you see it a lot in the control rooms. We start getting ready to land, and everybody relaxes a little bit. And that's a lesson I've carried with me, is you need to continue the vigilance there in the flight.
Communication is what it's all about. So everybody, we have to have the communication links. We didn't have it to the chase. Hot mic was a contributing factor. We didn't have it in the control room. We discussed things internally, was not transmitted to the pilot. We have to have an environment built where people can speak up when they think something's wrong. They don't have to be right. If they're concerned, they should be able to speak their mind, put their hand up, and we stop the train. And then we say, no, you weren't right, it's okay. Fine, we go on. We didn't do that. We never stopped the train.
We had a problem, and we didn't stop, not only testing, we didn't stop flying and come home. But you can't stop for every problem. I mean, that's unrealistic. You have problems in flight. The combination that went with that is we didn't understand the severity of the problem. So you have to understand your vehicle and the consequences of failures. And if one of those failures has a serious consequence, you need to stop and come home.
Clearly, there are lessons to be learned in the entire progression of events that led up to the X-31 mishap. And yet, the X-31 program did not end with that crash. The next chapter of its story is an equally important reminder of why flight test remains such a valuable step in proving a concept or technology, despite the hazards that come with the territory. The X-31 had been scheduled to fly at the Paris Air Show in June of 1995. But after the loss of one of the 2 X-31 ships less than 6 months before the show, it seemed an impossible goal.
Having lost the airplane, pretty much everyone thought that's it. Because flying the kind of maneuvers that this airplane can do at 500 feet sounded a lot riskier to me after you lose an airplane. The team really talked a lot about this and decided that it did not want to end this program on a low note. And so we made the decision to press on with the Paris Air Show.
A huge thing to sign up for was to take an airplane that just crashed and to turn it around to go do a low altitude, high angle attack flight demonstration. That took a lot of guts on everybody's part and a lot of good engineering work to make that happen.
We actually flew the X-31 84 days after the mishap. And this required the board to reach its conclusions, to write a report, for the team to react to all of the issues and problems and contributing factors brought up, solve the problem, and get it into an airplane and get it qualified for first flight. It was all done in 84 days. It does tell you about the quality of the team.
Cool. Landing a little right. And very covenant.
Totally different aeroplane which will demonstrate a most remarkable flying ability. It is the X-31 technology demonstrator.
After the mishap, I think the program made a spectacular recovery and made one of the finest appearances ever at the Paris Air Show. The airplane did things that no other airplane could do. The Russians had demonstrated post-stall maneuvers with the Cobra, but it was really an open loop maneuver. They pulled back on the stick and then you flew out of it at the end. Whereas the X-31 just demonstrated the ability to control all axes of the airplane pitch, roll, and yaw simultaneously while operating at the extremes of the flight envelope.
So, fantastic air show, absolutely the most spectacular I've ever seen, and I saw every one of them. And I stood with the crowd on some of them, and I was in the control tower on others, and out right underneath it at other times. But to be with the crowd and watch, even hardened veterans, military, had no concept of what it could really do, and seeing it was jaw-dropping for the crowd. It was spectacular.
The announcement that the X-31 was next to fly, as you look down the row of chalets, you see all the people coming out of the chalets, out against the railing to watch the flight.
If the events leading up to the X-31's mishap are a reminder of how much vigilance is required in order to mitigate the risks inherent in a flight test program, the X-31's Paris Airshow performance was a reminder of why those risks are still worth undertaking.
Flight test of all kinds is inherently dangerous. There are risks involved in it. Never can you or anybody else bring it to zero. Well, you can. That's keep the airplane in the hangar. Don't fly. Well, if you don't fly, you don't move forward, you don't discover, you don't prove things. So you need to take some risks, but you need to do it in a controlled fashion.
The reason we spend time on looking at these accidents is that there aren't many accidents. We don't lose many airplanes in flight research activities at Dryden. We haven't over the years. And so when you do have one, you better learn everything about it. In fact, you should do the same thing for close calls.
The lessons to be learned. Don't assume that they've been learned. We can always, at every new group, will have to learn the same lessons, and you don't want to do it the hard way with an accident. Safety is everybody's business. Flight test safety is everybody's business on the team, and there are no processes. You have to have processes, but there are no perfect processes that will not require good judgment from all levels of the program.
If you're a program that's been operating for a long time, potentially, you've got a lot of turnover, you're in your mature years, all your documentation is years old, maybe you better make sure that all your new people are as good as your old people, that you've reviewed your documentation and it's still correct and you all understand it, and that what you're doing today still makes sense from how you started. So maybe one of those, if you're in that area, you ought to take a look at yourself.
It always is clear what you should do after the fact, or should have done rather, and nobody thinks it's ever going to happen to them. To lose judgment, to lose this communication link, to not do the right things.
So what is the message? What is the message for the team? It may mean that I am a part of the chain, and that if I don't catch this, and if other people don't catch their mistakes, we will run through the entire chain and lead to a mishap. So it means that every individual in the program from beginning to end, no matter what the job is, from the highest level job to the lowest level job in terms of detail, they have to take it very seriously. And that's a message that you have to keep promoting, pronouncing, and explaining. It sounds trite, but everybody is responsible for safety. If you think some safety office analysis is going to find the things, they won't. Mishaps can occur everywhere, but the point is you have to fly safely, but fly.